All right, well, I'm recording to the cloud, so we are ready to get the class started. Well, first of all, I think as a class in general, you guys did a really good job with exam one, so good job. And I was actually surprised by the fact that most people got the notations done correctly. In other words, most people understand, the quantified expressions. It is the association of those expressions to injection and surjection that got many people. I was actually kind of surprised that the interpretation of the expressions was okay, but the relationship to injectiveness and surjectiveness and whether a function is a function, that's the uh, part where some people lost their points. So that was not expected. Okay, that was not how I expected the whole thing to turn out. All right. So with that said, we're going to move on to the current topic, which is we're going to finish up relations this lecture, and then we're going to move on to propositional logic, which is a really kind of bigger module. The relation by comparison is a kind of pretty small and insignificant module. So we'll go ahead and get started. Let's see. So I do have a relation homework assignment that is assigned today. It is due in 2 days, okay? But it's not really heavy duty. I think you guys can get it done. It's just a matter of, understanding the material, making sure that you understand all the concepts and be able to apply the concepts. All right, so can I answer your questions? Nope. Okay, all right. All right, so we are going to get back to relations, which is down here. This is the relation homework, so don't forget to get it done before class on Wednesday. So this way, we can get the spring break started without having to worry about, oh, do I have any homework to do over the break? All right. All right. So last time, we were talking about we finished basically all three. Let me go ahead and start up Joplin because that way we can take a look at where we left off. Okay. All right, so here's Joplin, and let's see, we have not talked about, oh, we have already talked about anti-symmetry. So we are done with the four basic properties of a relation. Okay, so we have reflexive. Reflexive means every element in X has to relate to itself using a relation. Typically, I use R to, for the name of the relation, which is basically just a subset of the Cartesian product of X and itself. Okay, so do we have any questions about the property, the reflexive property of a relation? Yes. Um, Okay, does anyone see a phone around you that is not yours? You remember where you sat? Okay. It is possible another student from your own class might have noticed it and took it with you. You can check the lab, which is room 301, and see if they have it. Mm-hmm. All righty. So that's reflexive. And then symmetry is a little bit harder to discuss because you're basically looking at the presence or the absence of a relation between two elements, but if one is missing, the other one has to be missing. If one is present, the other one also has to be present. Okay, so that's kind of what symmetry is. Transitive is based on three elements. Okay, basically you have to pick three elements where no matter how you pick the three variables or values for the variables, A relate to B and B relates to C implies A relates to C. Okay, that is the requirement in order to be transitive. And then anti-symmetry is about you have to find AB and BA, but if that is the case, then AB must be the same. Okay, that's anti-symmetry. All right, so do we have any questions about the four properties of relations? Okay, assuming there are no questions, and we're going to move on and talk about the last few topics. So the partial ordering thing we have talked about already. Okay, I used the beer commercial, to talk about partial ordering. In other words, partial ordering happens when you have three properties, basically happening, and once you have those three properties being true, then you have partial order. So we need reflexive, we need anti-symmetry, and we also need transitive. Symmetry itself is actually not needed in order to have partial order. So let me say that one more time. If a relation over R, excuse me, if a relation R over X is reflexive, antisymmetric, and transitive, then such relation R is also known to be a partial order or partial ordering, with respect to X. Is that okay? So once you understand the basic four, basically symmetry is not even used in this case. So with partial ordering, it is kind of nice, because you can compare certain things, but you cannot compare everything. This is basically the same discussion that we had, about being rich and smooth, or having only one, or having none of those. ALADA is just my abbreviation of at least as desirable as. Okay, that's what ALADA stands for. Okay, so total ordering is partial ordering plus one more. It also has to be comparable. R has to be comparable. And this quantified expression defines what comparable means. Okay, so let's check this out. For every way to choose two values to bind to variables E and F from X, ERF or FRE. So ERF is the same thing as saying EF as a tuple is in R, and then FRE is to say, the same thing as FE as a two tuple is in R. In other words, F and E, they have to be related somehow. Okay, so the direction does not matter in this case, but you need to have at least one of them to be present. Yes. It is not symmetric. Okay, yeah, that is correct. It needs to have at least one, but not necessarily both. So if you have both, then you have to question whether whether it is going to interfere with antisymmetry, because antisymmetry says ERF and FRE has to imply EF are the same. So if you have ERF and FRE and F and E are different, then you lose antisymmetry automatically. So you have to be very careful with comparable. All right. And then there's a whole bunch of AI generated questions, and I believe every single one of these was checked already. Yes, go ahead. Hmm? Okay, so the question is, can I use an example to illustrate comparable? Is that the question? How about I flip it and ask you guys to give me some examples of certain things that are comparable and certain things that are not comparable? Let me start up. Okay, I think Joplin is good for this, so I'm going to use Joplin, even though we don't really need all the nice formatting, but it's okay. Okay, so before we start off with what is comparable and what is not, it is important for me to define X. So I'm just going to use the regular typing here because I don't think we really need to get down to the mathematical symbols. So I'm going to define X to have, we'll simplify to only have two elements, A and B, okay? And can somebody tell me, oops, okay, it recognized the formatting, so it doesn't like that. Okay, fine, we'll do it the complicated way. There we go. Okay, so this is how X is defined, and I want examples of relations that are comparable. Okay, so now you guys can help me, find some examples. And I think I'm gonna put an empty line here. There we go. So R is, well, we can always start with the empty relation. Is the empty relation comparable? Okay, so let me go back, and show you what comparable actually means, and then I'll let you guys evaluate whether that is true or not. Okay. All right. So that is that. Okay. And we'll make it always on top, and we don't lose track of that. And then we switch back to Joplin. All right. So we are now evaluating the empty relation. Is it comparable or not? It is false. Okay. It is false because in order, oh, where's my definition? Or did I just close it? Where did I put it? Oh, hmm? All the way. No, I don't think that is the one. That's the mouse pad. I think I might have just lost it. Hmm? I'm looking at my other tab here. I do not have that terminal open anymore. Okay. I don't have that window open anymore. That's okay. Well, I can always go and grab it again. Okay. Do it one more time. Might have clicked the wrong key. Okay, open. Instead of saying on top, I might have closed it. So always on top. There we go. Okay, so now we should be able to get back to it. There we go. Okay. All right. So if this is how X is defined and this is how R is defined, what do you think happens to the existence of the element EF and the existence of the element FE? They're both going to be false. So now we have false or false, which is false. Okay, so that means this is more like an example of relations that are not comparable. Okay, all right. As I said a little bit earlier, can someone give me an example that is comparable with only two elements in it, AB and BA, and that's all we care? Since you asked the question, I'm going to put it back on you. Hmm? Yes, we're keeping the same X as a set, and we just want to define R, which is going to be a subset of the Cartesian product between X and itself. And we need to find one that is comparable, which means no matter how you choose values for E and F, ERF or FRE has to be true. Okay, so let's try that. Okay, so let me see if I understand your example. What about R equals to uh, A comma B? Is that it? Okay. All right. So if that is how R is defined, okay, now which side it belongs to, I have not determined yet. Okay, so don't copy this as if it is already determined. But what do you think? R is defined to be R is defined to have only one element, which is AB as a two tuple. Does it meet the requirement of no matter what we choose for variables E and F, that ERF and FRE or FRE has to be true? What if E and F are the same? Then if E and F are the same, then this OR is going to be false. So that doesn't meet the requirement, does it? So we're going to have to take this out and stash it over here because it is an example of something that is not comparable. Okay, yep, go ahead. It means for every way, sorry, say that one more time. Nope, we do not. We do need a few more elements, but not all four. Nope. Okay, let's check that out. Okay, because let's see what's going to happen to this example. Once again, do not copy it yet because we don't know whether it belongs here or not. ABBA. You guys are way too young to know what that is. Ask your grandparents. Okay, so if we have a set, let me go find where is it displayed because font size is a little bit too big. I can't find it. There we go. There we go. Okay. So if R is defined to be defined to have two elements, AB as a two tuple, BA as a two tuple, does it meet the requirement of this? No matter how you instantiate the variables EF, only knowing that they are both elements of X, ERF or FRE has to be true. So the question is, does this R, okay, this R that we just created, does it meet that requirement? Remember what I said about the earlier one? Remember why it does not meet the requirement? What if E and F are the same? So this one also does not meet that requirement for exactly the same reason. AA is missing, BB is also missing because E and F can both be A, E and F can both be B. So that means, okay, it doesn't work. We have to kind of stash this one to the other category. So we have not seen one that is comparable yet. All right, so I'm gonna let you guys to think about this a little bit more. Give me an example that is comparable when there are only three elements involved. Yep. Okay. Yep, that will work. AA, AA, BB, and AB. That will work. There's one more example, by the way. There's only one more example. Or two more, actually. Yep, go ahead. Okay. BA. And there's one more. That. So these are the four examples in this case that are comparable. When X consists of AB as two elements, then the three possible relations that are comparable are these three. There are no more. Yep. I'm not sure what you mean by that. I'm not really sure what you're referencing. The beer commercial? This one, I mean, right now it does not have anything to do with partial ordering because right now we are only focusing on one thing, which is whether it is comparable or not. Now, we can also try to apply the other ones, okay? There are a few observations that you can draw from this. Does comparable imply reflexive? I'll ask the question again. If R is known to be comparable, does that imply R is also reflexive? The other way to say is to say everything that is comparable is automatically reflexive. Can we say that? If you cannot say that, you have to give me a counter example of why that is, how it does not work. The answer is yes, it does imply. The reason why it implies that is because if EF are the same variable, which is one of the cases you have to consider, we need this to be true too. So that means an element has to relate to itself in order to be comparable. Now, is that the only requirement to be comparable? No. but is it one of the requirements to be comparable? Yes. So that means everything that is comparable is automatically reflexive. We good so far? All right. So now we also try to look at something else, okay? You can see how this one is comparable and also symmetric, right? Because we got AB and we also got BA. So now the question is, does being comparable and reflexive automatically imply it is not antisymmetric? Now, this is a kind of trickier question, okay? So I'll let you guys digest that a little bit first, okay? And I'll spout it out, okay? I just want you guys to understand what the question is asking. Okay, so does R being comparable and symmetric implies R is not anti-symmetric? What do you think? For any X, okay? For any X. Mhm. Think of the extreme cases. Think of the boundary cases. Okay, so let me make it more clear. Regardless of how X is defined, does R being comparable and symmetric imply R is not antisymmetric? Hmm? Is such a what? Well, since I'm asking here, it means it cannot be in your test anymore. Yes, not exactly. To be comparable means, no matter how you choose um, two values, okay, each value being an element of X, they have to relate to each other in some way, either this way or the other way. That's what comparable means. Everything has to relate to everything else, including itself. Okay, so I shouldn't say else. Yep. You only need one of them. It is an or, which means A or ARB or BRA. If you have at least one of them, it is already counting as, oh, AB are related. You don't need both. Yes. Yes. So if you have AB in X, then having AB will cover the case where D is A and F is B. Okay? So now let's go back to this statement here. Regardless, okay, this is important. Regardless of how X is defined, does R being comparable and symmetric implies R is not antisymmetric? So we have to look at one example, okay, a few examples. In fact, we look at the example that we just saw here, okay. This one is comparable and it is also symmetric. Let me point to the side that you're supposed to be looking at. This one here, it is comparable and it is symmetric, but it is not anti-symmetric because we have ABBA in the relation, and then this is not going to satisfy the requirement of ARB and BRA implies AB are the same because AB are distinct. So it's not anti-symmetric. And then if you go like, oh, okay, so the more elements we add to X, then the more it is not going to be anti-symmetric because when it is symmetric and comparable, it means not only does every element relate to every other element, the opposite relation is also in the set. Okay, yep. Hmm? It does not. It does not in general. So the exception to the cases is like, okay, when does it not apply? Even though most of the time it does apply, when does it not apply? So let me answer my own question here. So this is false, okay? Um, R being comparable and symmetric, implying R is not anti-symmetric, is true if and only if the cardinality of X is greater than or equal to 2. In other words, you need to have two elements in X first before this statement is true, before the implication is true. Okay, I just told you something, okay, and I claim it is true. What are you going to do? Ask ChatGPT, is tag right or wrong, right? No, can you show that? Okay, because all I have done is to say this works for everything except for two cases. In other words, can you show me that with those two cases that the implication is not true? So what two cases are we talking about? Okay, we are looking at this implication is true, but if and only if the cardinality of X is greater than or equal to 2, can the cardinality of X be less than 0? Can you have a negative number of elements in a set? No, you cannot, okay? So that means we only have two cases, when X is an empty set and when X only has one single element. Okay, so now we look at those two cases, okay? So if X is an empty set, what is the only relation you can have in this case? Hmm? The empty set itself, okay, is the only possible relation. There are no other possible relation. So now the question is, in this case, is this R, well, we can look at symmetric and comparable. We can look at symmetric first, that's the easy one. Okay, what do you think? What does symmetry mean in this case? You guys can look up the definition, and hopefully you have the definition written somewhere in your own notes at a corner, because you want to put all the definitions into the same place when you are, so that the next time we have an exam, you are already halfway done with your study guide. Yep. Okay. So I'm just quoting the definition here, okay, just so that we have something to look at when we evaluate whether this R is symmetric or not. Okay, so it means symmetry means E R F, left, right arrow, F R E, uh, close, and then close that. There we go. Okay. This is how symmetry is defined. Okay, if it goes one way, it has to go the opposite way. But if it doesn't go one way, then it should not go the other way either. Okay, it doesn't really even matter, okay? Because there's nothing in X. So the question now is, if there's nothing in X, is the quantified expression, is the universally quantified expression true or false? It is by default true. So that means an empty relation R with respect to an empty set X is in fact symmetric. Are we good so far? All right. So is anyone puzzled by what I just said? Oh, yeah, I was disappointed. I was about to explain that. Yes, yes. No, it means you cannot, it means there's no EF in X to begin with. So this expression is irrelevant. There's no case to consider. Okay, all right. Yep. If it is less than 2, then the implication is not true. That's the only thing, the implication that we mentioned earlier, that's the only concern that I have at this point. It can be symmetric, comparable, and anti-symmetric at the same time. Okay. All right, but I'm not done yet. Okay. Now the next question is, these are what was the other one? Comparable. Comparable. Okay. What do you think? We have R being an empty set. We have X also being an empty set. So the question is this R empty? Is it comparable? It is really the same kind of question because how do we define comparable again? Okay, well oh, okay. I don't have to look at it. I don't have to quote that. This is how we define comparable. So tell me, if X is an empty set, what do you think of the quantified expression where the mouse pointer is pointing to? But you answered the earlier question correctly. So what? There are no elements in X. X is an empty set. If X is an empty set, there's nothing to evaluate here. I might as well put a 0 here. It wouldn't make a difference. Okay, so it sounds like we did need a kind of warm up about how to look at a universally quantified expression where nothing is qualified to be evaluated. Okay, let's do that. Okay. So this is about how you read some of the material earlier because it relates to something that we have talked about like some time ago. Okay. So the side question here is, what does this mean? Okay. For all E in some kind of X and then P of E. Okay. I hope this looks familiar. I'm missing one close paren here. There we go. Okay. What does this mean? You can look at the right-hand side. Yep. That's one way, but this is really a shorthand. It is a shorthand of what? Okay, so this is me checking out whether you guys, one, study, two, retain the knowledge, because this one is a definition thing, okay? This one is not about understanding. This one is about definition because the notation is just a shorthand. Yes, say that one more time. Mm-hmm. That is still, you're basically just saying the same thing, which is not except not in mathematical notation, but it is a shorthand. This is a shorthand because we in one of the modules that talk about quantifiers, I said, okay, because we have to filter things so often that it does not help to write it in the long format just because it takes a little bit longer to type the long format. Yes. Thank you. Thank you. That is the answer. Okay, this is a shorthand of something that is even more elemental or foundational. Okay, so this is the original expression for every E in the entire universe. E as an element of X implies right arrow P of E. All right. So this the first one is just a shorthand of the second one because it takes me too much time to type an extra open paren, a extra close paren, and an implication symbol. Now, do you have to copy this? Well, what you should be writing down is, why am I not getting this from the earlier material? Now, I may sound harsh, okay? It may sound like I'm criticizing people, but I'm not, because that's a really legitimate question. Is where did it go when we talked about this? We did talk about this, okay? So the question is, where did that knowledge go? Now, this one does not require a lot of understanding because it really is how The second part, the long format, is defining the first part, which is really just, oh, okay, we can write it in a shorter format, but it means exactly the same thing. So given that we know this, and now we say, what if this x here, okay, what if this x here is an empty set? What happens to the entire universally quantified expression? Let's figure out. For everything in the entire universe, okay, that thing being an element of an empty set is going to be false. And it is on the left-hand side of the implication. So what does it tell you about the implication? The implication has to be true. So that is the reason why when you say something like this, okay, when X is an empty set like this, and we say for every E and for every F in X, blah, 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 I don't even care what the blah, blah, blah is. If X is empty, the whole quantified expression is guaranteed to be true. Is that connection made? Yes, no, kind of, okay. So this is really important, okay? How do we make the connection between the various parts, things that we have talked about in this class? That really is the important part, okay? Yes, how do you keep track of those connections? I'll give you a hint here, okay? It's called writing notes. You guys know that already. But it really is, okay? It really is. Writing notes is the way that you can keep track of the information. Now, does it guarantee that you can retain everything? No, not really. But that's exactly why you have to write it down, is so that you can revisit things, when you need to. All right. Yep. Yes. So R is supposed to be a subset of X Cartesian product with itself. But if X is empty, the Cartesian product itself is also an empty set. So the only subset of an empty set is empty set, is the empty set itself. Yep. Yes, that is part of the requirement of R, which is at the beginning of the relations module. Isn't it annoying that your professor actually wrote his own material and he remember where things are? I think it's annoyingly annoying. But it is important, okay? Because that means you have to read the module, you have to actually read the content in order to kind of absorb the material. All right. So let's go back and keep answering our question, okay? Because our question is not done yet, okay? The answer is yes, okay? Or let's just say true, okay? R is comparable in this case. It is symmetric, it is comparable. So now the next question is this R not anti-symmetric? Okay, okay, same deal, except this time we have to look at the definition of anti-symmetry. Do you guys remember the definition of anti-symmetry? Is it in your notes somewhere? Yep, yep. So in short, ERF and FRE implies E and F are the same. Okay, this is how we define anti-symmetry. So once again, X is an empty set. So I just spent a lot of time to talk about something that is not even relevant. Because if X is empty, I don't care what is inside the parentheses. The whole quantified expression has to be true. Okay, so the answer to this question is also true. Oh, I should say false, okay? Because I'm asking, is it not anti-symmetric? It is anti-symmetric. So is it not antisymmetric? The answer is false. So now we have true implies false, which means the implication is false. So that's why the earlier generalized statement is not true, because I can find at least one counterexample when X is an empty set. Yes? That it depends on it's inside what. Okay, so let me explain what I mean by that. So this P of E is currently inside a universal quantifier. What about the existential quantifier? So let's check it out. Okay, so I'm going to see if you guys at least can you relate this to how this is defined. Okay, there exists E in X such that P of E is true. Okay, this is also a shorthand, but it is a shorthand of what? Yep, it is a conjunction this time. That is correct. So this is a shorthand of for everything in the entire universe, E as an element of X and P of E in this case. It is a conjunction. So it is still a filtering mechanism. Oh, I just mistyped it. Sorry about that. There we go. So in this case, it is still a filter, but this time the filter is using a conjunction to connect to it with what we actually want to test. So in this case, if X is empty, then E is an element of X is automatically false. But if one side of the conjunction is false, the conjunction itself is also going to be false. So that means in an existentially quantified statement, and the filtering set itself is empty, then the existentially quantified statement is automatically false. So that's what I meant when I said inside of what, because is it inside a universally quantified statement or is it inside a existentially quantified statement? Okay. All right. So I'll be feeling comfortable, a little bit more comfortable with this stuff. Yes. Okay. All right, so remember I said two cases. I have just illustrated one when the cardinality of X is 0. So what if the cardinality of X is just 1? Okay, so we'll use another example here. Okay, so let's say X has one single element. I don't care what it is. I'm just going to call it A. So now the question is, does what we said earlier, is it true or not? Okay, so now we have to ask, is it true that um, R is comparable and what was the other one? Symmetric, imply R is not anti-symmetric. Okay. All right. So this is the question. All right. How many ways can we make R, in this case, R defined over X, to be comparable? There's only one way, right? AA is in R. Okay. So that is that also symmetric, by the way? Yep. Okay. So that means, so in this case, okay, so let me answer my own question here. The only possible R is R equals to a tuple with A and A itself. Okay, so this is the only R that is comparable and symmetric. In fact, this particular X only has two possible relations, the empty relation and this one. There are no other relations. Does that make sense? And how does it make sense? Okay, so if X only has one element, what is the Cartesian product of this X here? A comma A. Okay, so if that is the Cartesian product, how many subsets do I get out of that particular Cartesian product? 2, because of the power set thing, right? Okay, so the number of subsets is 2 to the power of the number of elements in the set where you want to generate the subsets. So in this case, since the set only has one element, that means we only have 2 possible subsets, the empty set and the entire set itself, okay? But the empty set does not qualify to be considered here because the empty set with respect to this x here is not comparable. A has to relate to itself in order to be comparable. So that means this is the only one that we have to consider. So now we have to ask the question, is this R anti-symmetric? Okay. Well, it has to be anti-symmetric, right? Because there's only one element in the entire X. So that means when we go back and look at anti-symmetry, no matter how you choose, you're choosing the same element of the set because it only has one element to choose from anyway, right? So that means ERF and FRE is guaranteed to be true no matter what you choose. What about E equals to F? Also got to be true because E and F have to be exactly the same element because there's only one element to consider in the entire set. So that means this is also guaranteed to be anti-symmetric, which means this implication is false because I have just shown that, oh, this R is comparable and symmetric, but R is symmetric. So R is not anti-symmetric, is false. So once again, the implication is false. I have found 2 counterexamples to the general claim that I made earlier. Do I need to? No, but I just wanted to show that, okay, there are 2 exceptions to that rule. But for every x that has at least 2 elements, then what I claimed earlier is true, okay? That claim being, if R is comparable and symmetric, that implies R is automatically not anti-symmetric. Is that okay? All right, yep. R is comparable in this situation. R defined as AA is comparable. Because for all, there's only one way to choose EF as elements of X. EF, they both have to be A anyway, because there's only one element in the entire X. Yep. It is symmetric because AA is in the set and AA is also in the set. So we have met the symmetric requirement. It is anti-symmetric. Yeah. Okay. Do you guys have any questions that I can answer? Mm-hmm. Implies R is not anti-symmetric. Yes. What is true? So what we have shown are 2 examples where R is comparable and symmetric, and also at the same time anti-symmetric. Yes. Yep. Mm-hmm. Oh, go ahead, sorry. Okay, the left side of what? The left side. Okay, but which implication? Are we talking about the implication that is highlighted here? Okay. So the anti-symmetric implication, which is this part here, if there's only one element in X, and we already know that X is comparable, that means this has to be true. we, okay, this part is, this is true, but this is also guaranteed to be true because there's only one element in X. So no matter how you choose, E and F have to be the same. So in this case, because both sides are true, that means you have not true or true, so the whole thing is true. Right. Okay. Yep. Sure. All right. So let's take a look at an example. Okay. So let's. Mhm. Okay. That's easy. Okay. So we'll look at X as only two elements, A and B. Okay. And I want you to define me R. Okay. Define R so that R is partially ordered, but not totally ordered. All right. So I'm flipping your question back to you guys and go like, can you find me such a R? Okay. So first of all, is it difficult to find this R? With only two elements in X, what is the cardinality of the Cartesian product of X and itself? 4. Okay. And then what about the total number of subsets of the Cartesian product of X and itself? 2 to the power 4, which is 16, okay, which is not too many, because we already want it to be partially ordered. And what does it take to be partially ordered? This is something that we talked about earlier in the class. There are three things that we need in order to be partially ordered. Reflexive. Okay, all right. So we want all of those, but we don't want comparable. Okay, that's the only thing that we want to say, oh, it is not comparable. So the question now is, can you find me a R over this X so that it is partially ordered, which means it is symmetric? No, I take it back, which means it is reflexive, anti-symmetric, and transitive, but we don't want it to be comparable. You only have one option here, by the way. Okay. So let's look at all the possible things. Okay. I think this is going to be an interesting exercise because I'm trying to illustrate how to think this through. Okay, so we look at our possibilities. Okay, possibilities of R. There are only 16 of these, okay, that are possible. And many of these we don't have to even think about. Okay, the first one is, oh, it can be empty. Okay. The second one is, oh, it is not empty. It has only one element, which is just AA in it. Then it only has BB, oops, is an element. Then it has, I mean, this is going to get really boring for a while. Okay. Okay, so B, A, and then we move on to the two element subsets. Okay. Do you guys really want me to go through this, or do you guys go like, okay, we get it? You want me to go through this? I should have written the program to do it. All right. So now we go like, okay, let's get AA. This is going to be so boring. AA and BB. And then we have AA and AB. And then we have AA and BA. Okay. And then I just go like, okay, let's copy this. And then we can go like, now we have AB and BB. And now we have BB and BA. And let's see, there's one that I'm missing, AB and BA, that's it, AB and BA. Okay, so now we have covered everything that has two elements in it. Okay, so shall we consider all the ones that have three elements in it? Okay, so I'm gonna go a little quicker this time. Okay, 6YY, and then just paste it here. Okay, So let me see where, okay, of the 6 last ones, which is from here. Okay, so this one is missing, oh, there are 2 sets of these. So I need another set of those, right? Okay, give me a second. Okay, 1, 2, 3, 4, 5, 6. Okay, okay, I'm trying to do this in a systematic way. Okay, okay, let me find where's the first one. AABB is the first one. Okay, there we go. AABB is the first one. There we go. Okay, so with this one, which one is lacking for all of these? Huh? So this one can use AB in it. This one can use B in it. Uh, there are only 4 possible things here, so I just overcopy things for sure. AB, BA, and BB, and there's only one more. Okay, which one am I missing? Okay, so we got AA, BB, AB. Oh, wait, these 2 are the same. Okay, so I just duplicated these 2. So AA, AB, and BA. Okay. AA, AB, BB. Okay, that covers those 2. So now we have AA, BB, AA, BB, BA. Okay, and there's one more. So we have AB, BA, AA, and then AB, BA, BB. That's it. Okay, those are the ones with 3 elements in it, and there's one that has 4 elements in it. Question? I thought I saw a hand. I hope it wasn't a hand to go like, this is so boring. I'm about to fall asleep. That's it. Okay. There's only one with 4 elements. Does that make sense? Okay. So I claim that there are 16 of these up to this point. Okay. So let me zoom out a little bit. Okay. There we go. Let's count. Are there 16 of these? Okay. 1, 2, 3, 4, 5, and then 6 of these. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. I feel like the count in in Sesame Street. Maybe one day I will paint myself purple and wear a hook little nose and a little monocle. No. All right, so there are 16 of these. Okay, fine. Which one of these 16, what was I about to illustrate? Oh, we need to find um, the 2 relations. No, the one relation. There's only one relation that is partially ordered. Okay, so now we will do it by the process of elimination, okay? Now, do we have to do things like this every single time? The answer is no. But why do we do things like this the first time? So that we can see the pattern, okay? So noticing the pattern is important. Okay, so I think we can eliminate everything that only has 0 or 1 element. Because in order for this to be reflexive, what do we need? What does reflexive mean when X has A and B as elements in it? What do we need in the relation in order for the relation to be just reflexive? AA and BB. That's how, because every element has to relate to itself to be reflexive. So that means we can now say, oh, okay, the first 5 cannot be it, okay? So basically we draw a line here, okay? The following maybe reflexive, okay? But everything before cannot be reflexive because they don't even have enough elements to begin with. Okay, this one is reflexive. This one is reflexive. And everything else with only two elements cannot be reflexive because it takes AA and BB to be reflexive. All the other five do not have at least one of AA or BB, right? So that means this is the only one that is reflexive of all the ones that have only two elements. Does that make sense? Okay. So now we go like, oh, wait, okay, if it's already reflexive, can it also be meet the other two requirements to be partially ordered? Remind me again, what are the other two requirements to be partially ordered other than reflexive? Okay, transitive. Yep. Okay. So now we look at this one and we ask, is it anti-symmetric? Okay, now you have to tell me why you think it is not. Say again? Mm, well, okay, when you evaluate whether it is anti-symmetric, you have to bind E and F to every possible element in X, in every combination, okay? But somebody said it is not anti-symmetric. So that person now has to tell me, how do you choose E and F to show me that the relation that we are looking at here is not anti-symmetric? Okay, so who said it was not anti-symmetric? Okay, so how do you choose E and F? E equals to, okay, but you're not answering my question. I know how bad that sounds, but that's exactly the truth. You're not answering my question. My question was, what was the counterexample to show that it is not anti-symmetric? What value of E and what value of F makes ERF and FRE implies E equals to F false? You have to show me one example. Yep. Hmm? Okay, but you still have to tell me how do you choose E and F? Okay, so let me just go like this. Okay, if this R is not anti-symmetric, then find E and F such that, okay, E, R, F, and F, R, E implies E equals F is false. Yep. It is anti-symmetric. That is correct. Hmm? But you said it is not anti-symmetric. It is not, it is anti-symmetric. That is correct. I cannot remember. Now, obviously, everything is still being recorded, so we can always go back and check what I said. Okay. All right. So I misunderstood what you said then. Okay. But it is anti-symmetric. Okay. So we can go back and say it is anti-symmetric. So we are now one step closer to what we want. It is true. For every way you choose EF, it is true. Okay. So what was the last requirement? Transitive. Okay. So now the question is a transitive question. Okay. In other words, this time you have to instantiate three variables, E, F, and G, such that no matter how you instantiate the values of E, F, and G, ERF and FRG implies ERG is true. Okay, let me show you the expression first, and so that you guys can evaluate it. So it means ERF and FRG implies ERG is the whole thing is true. Okay. Okay. So I just quoted the transitive definition here. So can someone tell me whether AABB is transitive or not? It is transitive. Okay, so I think we have found our we have found a relation that is at least partially ordered. Is it totally ordered? It is not totally ordered because it is not comparable, and it's not comparable because if you look at this particular relation, why is it not comparable? What is to be for a relation to be comparable? Every element has to relate to every element, including itself. Now, obviously, A relates to itself, B relates to itself, but do A and B relate to each other in one way or another? Nope. Okay, so it is not comparable, and therefore it is not uh, totally ordered. So this is partially ordered, but not totally ordered. So let me go back and redo the whole thing. Is partially ordered, but not totally ordered. So we have answered the first part of that question. So now the question is, of all of these possible relations, which one or which ones are totally ordered? Yes, go ahead. No, the last one is actually not. This one is not even partially ordered. It is not antisymmetric. This one is not antisymmetric, so it's not even partially ordered. And if it is not partially ordered, it cannot possibly be totally ordered. So now I'm asking you, which one is totally ordered? Or which ones are totally ordered? Okay, so we'll take a look. This one is totally ordered because it is reflexive. It meets all the requirements. This one is also totally ordered, and that's it. So with only two elements in X, we have one single relation that is only partially ordered but not totally ordered, and then we have two relations that are totally ordered. So is that process okay? Does everybody understand why everything else are not even partially ordered? Are we good? All right. I'm gonna double check anyway. Let's pick on this one. What are the reasons why it is not partially ordered? So I'm talking about this one here. It is not reflexive, and it is also, in fact, there are three reasons why it is not partially ordered. It failed every single possible test. It is not reflexive because we are missing BB. It is not antisymmetric because AB and BA are both in it. Okay, it is not anti-reflexive, anti-symmetric, and it is not transitive either. Why is it not transitive? There's a counterexample. But what is it? What is missing here? What is missing that caused this one to be not transitive? It's missing BB. That's right, because BA, BA, and BA and AB, but no BB in it. So that means if I choose E and G to be both B's and then F to be A, that particular expression would be false. Is that okay? All right. So I hope this kind of really helps to illustrate all the concepts. Okay, so the properties of a relation would be reflexive, symmetric, which is not really terribly useful. Okay, symmetry is not really that useful. We have anti-symmetry, we have transitive, and then we have comparable. So those are the 5 properties of relations that we have talked about in this class. Yep. Um, that is a good question. The only reason why I see how it is relevant is when you have symmetry and comparable for any set X that is reasonable, that has at least two elements, that automatically guarantees it is not anti-symmetric. That's the only thing I can think of. Any other questions? All right, so I'm gonna have to ask, do you guys have a question that I can address? Because if I can hear you, everybody who's in front of you and also to your side can also hear you. So I'm gonna have to ask you to ask me instead, please. Okay, okay. So can you find a different way so that it does not distract the rest of the class? Okay, okay, all right, cool. All right, so that pretty much concludes relations, and that's why we are gonna have our relation homework assignment, which is right here. It is due on Wednesday. It's not really super heavy duty in I mean, we went through basically all the important examples already. Okay, so this one is not super duper hard. Um, and then we are going to transition to talk about propositional logic if there are no additional questions about relations. Yes, next week is spring break. You guys are welcome to come back to the campus, but I won't be here. This is me answering the question like really directly, but not in a useful way. That is my talent. This is my number one talent is to answer a question in a way that is useless. Yes. Hmm? No, that is not true. The DSPS center will still be open. So a lot of other than instruction, a lot of the resources on campus is still open. So you kind of have to check first, okay? If you want to access some kind of resource on campus, check with them whether they will be open, next week or not. I don't know about the library, because it might or might not be open. Mhm. All right, so we are moving on to propositional logic, okay? So this one is kind of interesting because I'm not sure. I think I did show you guys an article about how the AI approach is hallucinating and how they are using ancient Greek logic to help the AI to stay on track when it comes to reasoning. Okay, so let me see if I can dig up that particular article again. Okay, so AI, hmm? uh, ancient Greek logic. Oh, it did? Oh, say again? Oh, okay, I see. Okay, got it. Okay. Thank you. All right. Well, the ancient Greek logic that this article is referring to is propositional logic. So I want to bring some relevancy between what we talk about in this class and what you guys have to probably understand when after you graduate and try to get a job. So I think this is some kind of relevancy. Okay. So I'll leave it up to you guys to read this particular article. So now the question is, what kind of ancient logic are they talking about? Well, it really is just propositional logic. And but the way I organize this module is a little bit different compared to most other textbooks that talks about propositional logic. Most other textbooks will talk about propositional logic from the human perspective, okay? In other words, how many operators do we know? Well, we have conjunction, disjunction, negation, and then we have implication, we have if and only if, the double-sided arrow. And do we have any restrictions as to how these things can be nested? In other words, can we nest a disjunction as the first component of an implication? Yeah. Okay, so where we have there's no real restriction as to what construct can be nested within what other construct when it comes to the human perspective of propositional logic. Is that okay? So you can compose some really complex expression in some really weird way, and it would still be valid, okay, syntactically correct, and perhaps even meaningful. But to prove theorems like that is very difficult, okay? We don't have enough time to really get into the technical detail today, so I'm going to describe it first, okay? So you guys will probably remember the analogy. The human way of proving theorems when it comes to propositional logic, or at least the system itself that allows us to prove theorem, is trying to find a needle in a haystack. Okay. In both cases, it is finding a needle in a haystack with one important difference. How big is the haystack? Okay. So the traditional view on propositional logic has an infinitely large haystack, and you're supposed to find a needle in an infinitely large haystack. What is the problem of that description? Well, can you even confirm? Can you ever confirm the needle is not in the haystack if the haystack itself is infinitely large? You cannot. So that means you can keep working and keep working and keep working. You may not find the answer that you need to find, but it's no confirmation that the answer that you were seeking is not actually in the solution. Is that okay? So the way I'm going to transform propositional logic is to put certain restrictions on it so that the only valid expressions are what I call CNF, conjunctive normal form. The way you understand the conjunctive normal form is rather easy. The outermost or the last operation can be a gigantic conjunction. So now the question is, what are we ANDing? Every component that you're ANDing by itself is a disjunction, a OR. And then the next question is, what can be in an OR? Well, what can be in an OR is either a variable, a Boolean variable, or the negation of a Boolean variable. That's it. So it is a very rigid structure, but once I make that transformation, the problem is suddenly changed because now your haystack is now finite, which means if the needle is not in the haystack, you can search through the entire haystack and go like, well, there's no needle here. Tack, you were trying to trick me, huh? Well, you cannot trick me anymore because the haystack is not infinitely large anymore. I can search through the entire haystack and confirm that the needle was never here to begin with. Okay, so that's kind of the um, overarch of this particular module is how do we first talk about just regular propositional logic, and then two, how do we transform that into a way so that it becomes a solvable problem? Yes. The needle is okay. So the proverbial needle is not so much whether it is here or not, it is whether it can be derived. So there's one more thing that is important before we depart today, which is what does it mean when you were asked to prove a theorem? What does it mean? Hmm? Aha, I like that. Implies. Okay, there's an implication in the whole thing. Go ahead. You can use a counterexample to prove something is false, but to prove something is true, you cannot use a counterexample. You can prove by contradiction, which is a different thing. Yes. Okay, it's kind of like that. The whole thing about proofs is it is a gigantic mash of implications. You start with what is given or known to be true. Okay, so those are the seeds. And then you use implication to keep going to derive additional expressions that are also true until you get to the one single expression that you were asked to prove. So that means you have to be able to trace from the expression that needs to be proven to be true, you have to be able to track everything back to everything or things that are given to you to be true, things that are axiomatic or just given. Yes. That is okay. Well, that one is not related to propositional logic or what we are trying to do. So imagine this, okay? So before, I know we are running a little bit over time. So imagine this, okay? There's only a finite number of expressions, okay? So I'll give you, once we get to CNF, I will tell you that there's only a finite number of CNFs. I will tell you that certain CNFs are known to be true to begin with. The question is, can I use the ones that are known to be true to begin with to imply one specific one to be also true? So the question is not whether it's there or not. The question is it implied by everything that is already known to be true? That is the question. Can we label it to be true? Can we label it to be, this can be implied by everything that is known to be true? So we are running out of time, so we'll continue this on Wednesday, but please try to read the chapter as much as you can before Wednesday, because that will certainly help a lot. All right, thank you. And I am going to stop the recorder and sign out.